Let me share my screen. All right, so today we're going to talk about basic probability. Hello, Zoom user. Welcome. Um, Zoom user, can I get your name? What should I call you by? All right, Zoom user. Well, so today we're going to talk about basic probability. So what is probability? Probability is simply, the chance that something happens, very intuitive. And if you want to talk about it in terms of mathematics, it is simply the number of successful outcomes divided by the number of possible outcomes. So in other words, it is simply the number of desired outcomes divided by the number of total possible outcomes. So let's give an example of that. What do we mean by this? So what is the probability that when you roll a standard six-sided die, you get an even number? So how will we calculate and solve this problem? Well, from the previous slide, we know that definition of probability is simply the number of successful outcomes divided by the number of possible outcomes. So how many successful outcomes are there in this case? Well, on a standard six-sided dice, you have 1, 2, 3, 4, 5, 6 numbers. And among them, exactly 3 of them are even, 2, 4, and 6. Therefore, there are 3 successful outcomes, and that's out of a total of 6 possible outcomes. So the probability is simply 3 divided by 6, which is 1/2. And here's the solution written out. Like I just said, there are 3 even numbers in a six-sided dice, right? 2, 4, 6. Pretty obvious. There are a total of 6 possible numbers, 1, 2, 3, 4, 5, 6. So the answer is simply 3 divided by 6, which is 1/2. All right, let's look at an example that's slightly harder. So in the standard deck of cards, right, like the playing cards that you would normally play with, a normal deck of cards has 52 cards. And these 52 cards are divided into 4 suits, each of which, each of the suits are, so 2 of the suits are hearts and diamonds. And these 2 suits are cards, are red, right? When you have a card, you have like the red hearts and the red diamonds. And the other 2 suits are spades and clubs. And these are black. It should be pretty intuitive, right? Like when you have a set of playing cards, you have 4 different types of shapes. 2 of them are red, hearts, and diamonds. The other 2 are black, spades, and clubs. So now the question is, the cards in the deck are shuffled into a random order. So what's the probability that when you take the 2 cards on top, the 2 cards are going to be red? So in other words, if I put the cards in a random stack, what's the probability that the 2 cards on the very top are red? So why don't we think about this for a second? If you have an idea of how to solve this, feel free to type it into the chat or just yell it out. All right, so why don't we solve this? So let me just go ahead and show the solution and I'll explain it to you guys step by step. So again, probability is a very simple concept, right? Probability is simply the number of desired outcomes over the number of possible outcomes. So why don't we calculate the possible outcomes first? So for the first card, you have 52 choices, right? There's 52 possibilities for what the very top card is. After that, there's 51 possibilities of what the second card is. So that means the total number of possible outcomes for the top two cards is 52 times 51. This invokes the concepts we learned, like 2 classes ago. So if you have any questions, just type into the chat. So now let's calculate the successful outcomes. We know that there are 26 red cards and 26 black cards, right? So the number of successful outcomes is simply 26 times 25. And the reasoning is actually exactly like 52 times 51. Because if you want the cards to be red, you have 26 choices, right? For the top cards, you can only have 26 different types of cards that are red, right? So you have 26 choices. And then after the top card, you now have 25 red cards left. So in order for the second card to be red as well, you only have 25 choices. So that's 26 times 25, right? So finally, we're going to divide the successful outcomes by possible outcomes, which gives the answer of 25 over 102. All right, so hopefully that makes sense. If you have any questions, again, just shout out. Okay, so now there's a different solution. And this solution is going to involve combinatorics. Combinations, which we learned a while ago, but as a brief reminder, combinatorics combinations are written in this notation, 52C, like this one right here, right? And what this is basically saying is the number of ways to choose 2 objects from 52 objects, right? And back 2 classes ago, we use committees to talk about combinations. And so you can basically think of this expression here as the number of ways to choose 2 volunteers from 52 students, and the order in which you choose them does not matter. So we calculate combinations like this. You start by pretending that order matters, right? 52 choices times 51 choices. However, the order doesn't matter. So you divide by 2 factorial, which is the number of ways to arrange them, to get the number of distinct combinations of 2 people out of 52. All right, so now going back to possible outcomes, the number of total possible ways of choosing 2 top cards is just 52 choose 2, right? Because you're simply choosing 2 cards out of 52. The order doesn't have to matter. So you have 1,326 ways of choosing 2 cards, but that's the possible outcomes. So now we want to find the successful outcomes, and we know that there's only 26 red cards. So we want to choose 2 red cards out of 26. And that's just 26 choose 2 again, right? Because you're choosing 2 objects out of a set of 26. So it's just choosing 2 volunteers out of 26 students. So that's just 26 times 25 over 2 factorial, which is 325. So if you divide 325 by 1,326, you would end up with 25 over 102 right here. And luckily, we did indeed get the same answer as we did before using the first solution, which is right here. And indeed, if you've been doing math for a while, you know, the more ways you can use to solve a problem, the more likely that you got the problem correct. All right, so if you noticed, in these 2 solutions, the only difference is that in solution 1, the order matters, right? The way we're calculating this is that we're choosing the first card first and then choosing the second card, right? So for example, if the top card was a red heart 4 and the second card was, I don't know, a red heart 5, then the way we calculated it is that if you have a red 4 and a 5, I'm just gonna call them 4 and 5, you get the idea. If you have a 4 and a 5 versus you have a 5 and then a 4, there are 2 different outcomes, right? because 4 is on the top, 5 is on the second, and versus 5 is on the top and 4 is below the first card. So in the first solution, the order of the cards do matter, right? We're considering the order of the cards. However, in the second solution, we do not care about order, right? Because in combinations, you're fundamentally just choosing 2 objects from 52 objects. I don't care if I got the 4 first and then got the 5, or if I got the 5 first and then got the 4. It doesn't matter. So indeed, in this solution, the order the cards are arranged does not matter. The only thing that matters is the 2 cards on your hands, right? So what's the main idea here? The main idea is when you calculate probabilities, you can choose to calculate the number of successful outcomes and the number of possible outcomes with regard or without regard to order. However, you must be consistent with the 2. So just to elaborate on that, let's go back to the first solution. Notice how when we calculated the possible outcomes, we accounted for the order of the 52 cards, right? The order matters for possible outcomes. But when we calculated the successful outcomes, we also accounted for order, right? We did 26 times 25. We didn't divide by 2. So as you can see, if you want to include order, then you have to include accounting for order in both possible and successful. You cannot simply include order in one case and not include it in the other, because that would just mess up the calculation. So again, when you calculate probabilities, it's pretty freestyle, but all you have to make sure is that whether or not you're accounting for the order in which objects are arranged, you have to be consistent in successful outcomes versus total outcomes. All right, so now there's another way to calculate probability. So as we have learned on the very first slide, dividing successful outcomes by total outcomes gives you the probability of an event happening. However, that is not the only way to calculate probability. There's another way, because if you have a series of independent events, note that it has to be independent. You can also calculate the probability of the overall event by calculating the probability of the individual sub-events. So as always, when you put math into English words, it's super confusing. So let's look at an example to solidify and make this idea more concrete. So remember the problem we just did. This problem. You have 52 cards and you rearrange them and you pick the top 2. And you want to find the probability that the 2 cards on top are red. But we don't want to do all this stuff. We don't want to do 52 times 51. And we don't want to do like 52 choose 2. It's too much calculations. All right, so here's a quicker way. So the probability of the first card being red is 1/2, right? Everyone agrees. There's 26 cards. There's 26 red cards, 26 black cards. So the probability of choosing any random card is simply 1/2, right? Because half the cards are red, half are black. Pretty intuitive. So now that we have the first card, and it is red with probability 1/2. So given that the first card is red, what is the probability that when we pick up the second card, it is also red? Well, now we invoke the first idea. So since we already picked up a red card, there's only 25 now, right? Makes sense. You have 26 red cards, you take away 1, so there's 25. But that's the successful outcomes. There are a total number of 51 cards left because you took away 1. So 52 minus 1 is 51. So that means the probability of the second card also being red is 25 divided by 51. Right? So then the probability of both cards being red is simply 1/2 times 25 over 51, which is 25 over 102. And this is the answer we got earlier. So you see, this is a much better method of solving that problem, because the only calculation we did here is like write down two fractions. It's so easy. So this shows you, a very good method of calculating probabilities, which is multiplying probabilities together. And this way you can calculate the overall probability of an event happening. All right, so now let's do a harder example. So I'm gonna play Joyce in a game of chess. Does any of you play chess? It's a pretty fun game. So I'm gonna play 4 games with her, right? 4 games, sorry. We're gonna play 4 games, and Joyce is unfortunately a much better chess player than I am. And in any match that we play, she has an 80% chance of winning because she's so much better at chess than me. Okay, so now the question is, if I play Joyce in 4 games of chess, what is the probability that Joyce will win all 4 games? It's pretty intriguing. What is the probability that Joyce will win the tournament? So there's so many words in this problem, but it's really just a simple concept. It's the concept we used like 2 minutes ago. So here's the solution, right? The probability of Joyce winning the first game is 4/5, right? Because she has an 80% chance of winning any given match. And 80% simply converts to 4/5, right? Should make sense, pretty intuitive. So the chance of her winning the first game is 4/5. The chance of her winning the second game is also 4/5, right? Because for any game that we play, Joyce's chess skills dominate my chess skills, and she has a 4/5 chance of winning. So the probability of her winning the second, third, and fourth game are all 4/5, right? So if she wants to win the entire tournament and win against me in all 4 games, she has to win all 4 of the individual games. So that means the probability is simply 4/5 times 4/5 times 4/5 times 4/5 equals 256 over 625. So again, this is a demonstration of the concept we learned earlier. And that is, probability doesn't have to be calculated always using successful over total, right? You can break the problem into individual tiny pieces and then solve it. And it's so much easier. All right, so we multiply probabilities. But what about adding probabilities? So as we have seen, you can only multiply probabilities when the events are completely independent, right? If the events do not affect each other and you're trying to find the overall probability, then yes, you can simply multiply the probabilities. However, when the question asks the probability of event A happening or another event B happening, you add the probabilities of each event. So it's the probability of A plus the probability of B happening. And note this notation is like P parentheses A. So this is simply mathematical notation. It simply means the probability of A happening and the probability of B happening. So this concept should be pretty intuitive. It's like, what is the chance of me eating a fruit? What is the chance of me eating an apple or a banana? If there's a 1/3 chance that I would eat an apple in any given day, and I will eat a banana at any given day, then it's simply the chance of me eating one plus the chance of me eating the other, right? It's pretty intuitive. So let's see an example of adding probabilities. So let's say that I have a really fancy bag with 12 fancy little marbles. We have 5 red marbles and 7 blue marbles. Very colorful, very pretty, it's very made of glass, very smooth. And a marble is selected and taken out of the bag. So I grab my hand into the bag and randomly pull out a marble. And then after that, out of the remaining 11 marbles, I take another one. So what's the probability that both of them are the same color? So in other words, what's the probability that both of the marbles I take are red or both of the marbles I take are blue? Think about it for a second. Think about how you would add probabilities in this case. All right, let's solve this problem, shall we? So here's the solution, right? So as we have mentioned earlier, this is an or question, right? The word or involves, and it's asking the probability of event A happening or event B happening. And in this case, the events is simply one being both of them being blue, the other being both of them being red. So all you have to do in this case is calculate the probability of one of them being red and one of them being blue, and then simply add the probabilities together, right? I'm sorry, not one of them, both of them being red and both of them being blue, and then add the probabilities together. It's super simple. So what's the probability that both of the marbles are red? Well, this goes back to our card problem, doesn't it? So we have 5 red marbles out of 12. So that's, for the first choice, we have 5 desired outcomes out of 12 total outcomes. So the possibility of me getting a red marble, which is my favorite color, not really. Probability of me getting a red marble in my first pick is 5 over 12, right? Successful over total. Keep that in mind. It's super important for probability. And then after I get that first marble, there is now 4 red marbles left, right? And there's a total of 11 marbles. So the probability of the second event is 5 over 33. And note how we're multiplying probabilities here, right? This is like the idea from before, multiplying probabilities. And then now that we calculated the probability of them being both red, we also have to calculate the probability of them being both blue, right? Because it says, what is the probability of them being the same color, not both of them being red or both of them being blue? So we have to calculate, we have to account for both of the cases. So the calculations for both of them being blue is literally the same steps as both of them being red. It's simply successful over total times successful over total, right? We have 7 blue marbles, 7 over 12, remaining 6 over 11. So multiply that, you get 7 over 22. Add them up and do a little algebra, not algebra, arithmetic, you get 31 over 66, which is just slightly under 1/2. All right. Again, if you have any questions, shout out or just type in the chat. Okay, now complementary probability. So Lloyd, you would remember this. Remember back when we were talking about combinatorics, we talked about complementary counting, right? It's like the idea of instead of counting the number of ways to do something, we're going to count the number of ways to not do something and subtract that from the total number of ways of doing something, right? So probability works the same way. So instead of finding the probability of an event happening, sometimes it's easier to find the probability of an event not happening and then subtracting that probability from 1. And in other words, sometimes directly finding the probability of an event happening is pretty difficult. So instead, we're going to find the probability of it not happening and then subtract it from 1. And this is a super important concept. Note that probability always has to be a number from 0 to 1. It will never be less than 0, and it will never be greater than 1. Hopefully that makes sense, because, for example, how would you have a negative probability, right? It doesn't make sense. Like, what is a negative probability? What's a negative chance of something happening? It doesn't make any sense. And how would you have a probability of that's greater than 1, right? It doesn't make sense, because a probability of 1 is something 100% chance of happening. So you do the event 100% chance. I mean, sorry, you perform the experiment 100 times, and 100 times out of 100 times, the experiment works the way you want it to. So that's 100%. So 120% does not make any sense, because you can't have 120 successful experiments when you only did 100 experiments, right? It doesn't make sense. That's like saying that you chose 100 apples and 150 of them are blue. I mean, 150 of them are green apples. It doesn't make sense, right? It doesn't make sense. So probability always has to be between 0 and 1. Okay, so now let's put that idea into practice and do a quick example. So this is a problem from the 1991 AJHSME, which is like the precursor of the AMC contest. And it's a pretty neat little probability problem. So each spinner is divided into 3 equal parts. The results obtained from spinning the 2 spinners are multiplied. What is the probability that this product is an even number? So basically it's saying that I'm going to spin these 2 wheels randomly, right? Totally random. It's going to land on one of 3 numbers, totally random. So for example, I land on 1 and 4, and you're going to multiply the two numbers together. So you get a product of 4. So they're asking, what is the probability that the product is always an even number? What's the probability that you randomly go into the wheel and you get an even product? So let's say that we're going to directly calculate this probability. I'm not going to lie, it's going to be pretty difficult, because in order for a product of 2 numbers to be an even number, either one of them can be even, right? For example, if I have 2 times 3, one of them is even, but the answer is even, right? It's 6. It's an even number. Or if I have 2 times 2, both of them are even, so the answer is also even. The only way that it won't be even is if both of them are odd. So 3 times 3, which is 9. So as you can see, if we were to calculate the probability directly, then we would have to account for both of the wheels varying between even and odd. And then we have to calculate the chance of both of them being even and subtract that from the probability, because I'm over counting. That actually involves a concept called pi. And we might go back to that if we have time. So, but nevertheless, let's practice complementary probability right now. So the way you would do this is, instead, you're going to calculate the probability that the product is an odd number, because that's so easy. If it's an odd number, both of these have to be odd, and that's simply a multiplication problem, like this. Instead of finding the probability of the product being odd, it's easier to find the probability of the product being odd. Sorry. Instead of finding the probability of the product being even, we're going to find the probability of the product being odd. So again, as I have already stated, the product is odd if and only if both factors are odd. And as a quick mathematical tangent, this phrase is going to appear often in your mathematical career. So if and only if is a two-way statement. For example, basically what's saying is the product is odd if both factors are odd. Also, if both factors are odd, then the product is odd. So basically the statement works both ways. But if and only if statements, they, because here, let me type it into a text box here. So the if and only if statement is really a combination of 2 statements. First of all, it's saying that the product is odd if both factors are odd. That's the first statement. But it's also saying something else. It's saying that both of the factors factors are odd if the product is odd, right? It's saying two different statements. And indeed, they're called converses of each other. Converses, just like the shoes converses, but except it's math. So it's called converse statements. So statement one is a converse of statement two and vice versa. But a converse of a true statement isn't always true, right? For example, if I say, I don't know, if, okay, so let's say this. Here's a really good one. So if you live in California, you live America, right? That's pretty obvious. If you live in California, that's an American state. So you have to live in America. The converse of that statement would be, if you live in America, you would live in California. That's so false because there's 49 other states in America other than California. So as you can see, the converse of a statement isn't always true. So, yep, that's just a mathematical tangent. Back to probabilities. So there are two factors on the left spinner that are odd, right? It's just 1 and 3. Pretty intuitive. And then on the right spinner, there's only one odd factor, 5. So that means it's simply 2/3 times 1/3 equals 2/9, right? It's going back to the card problem. We have 2 odd numbers over 3 total numbers times 1 odd number over 3 total numbers gives you the answer. So that means the desired probability of both of the numbers being even is simply the probability that both of the numbers are not odd, which is just 1 minus 2/9, giving us 7/9. Right? Pretty easy. All right, I think we're gonna have time and we're gonna come back to this and I'm gonna show you guys a really cool solution that involves pi, which stands for principle of inclusion and exclusion. But for now, let's do a couple more practice problems. Now that you've learned everything, time for some practice. All right, so here's another spinner problem. It's so fun. Okay, so this is a problem from the 1989 AJHSME, which is again the precursor to AMC. It's my favorite contest. I'm joking. Problem 25, pretty difficult, but you guys can solve this. So every time these two wheels are spun, the one on the picture, it's pretty dark for some reason. I couldn't fix the slides. Two numbers are selected by the pointers. See this little black pointer thing? So the spinner, you spin it and it points to a number. So what is the probability that the sum of the two selected numbers is even? What is the probability that when you take two random numbers from two spinners, they add up to an even number? It's intriguing. I'm gonna give you guys 30 seconds to think about this. If you have any thoughts or a complete solution, type into the chat or tell me and by unmuting. Do this. Solution. So pretty intuitive. If you want the sum of two numbers to be even, the two selected numbers have to have the same parity. Oh my God, here's another fancy mathematical word. So what is parity? Parity is basically the odd slash evenness of a number, right? So it's basically like a fancy adjective for describing whether a number is even or odd. So basically, in normal English language, what this sentence is saying that for the sum of two numbers to be even, the two selected numbers have to be either both odd or both even. So you could solve it by, calculating a probability that they're both even and a probability that they're both odd. But there is a much better way. There is a very clever way that you just have to think about it. So the first spinner has 2 odd numbers and 2 even numbers, right? Let's fact check this a bit, right? So the first spinner has 4 and 8 even, 3 and 5 odd. That's right. Okay, so that means no matter what the second spinner is, there is a 1/2 chance that when you spin the first spinner lands on a number with the same parity. Right? Does that make sense? Since the first spinner has 2 odd numbers and 2 even numbers, no matter what the second spinner spins, there is always a 1/2 chance that the first spinner will land on a number with the same parity. So the probability is simply 1/2. That may be a little confusing. So here, let me explain this in a little bit more further detail. So let's say that you chose a 9. You got a 9, right? So that's an odd number. So on the first spinner back here, you have 2 odd numbers and 2 even numbers, right? 8 and 4, 3 and 5. So that means when you spin the first spinner, there's always a 1/2 chance that's going to be odd and have the same parity as 9, right? There's a 1/2 chance that's going to land on 3 or 5. But let's say that you didn't get 9. Let's say that you got 6, an even number. So now back to this first spinner. In order for the sum to be even, the number has to be 4 and 8, 4 or 8. But that's just a probability of 1/2, right? So that means the probability is simply 1/2. So easy. It's a really easy way of thinking about this problem. And in general, for probability problems, you should always search for, like this, think about a solution so that you don't have to do all these calculations. But just for the sake of practice, we're going to solve it the harder way. So as we have stated, the probability that the sum of the 2 selected numbers is even is either both of them are even or both of them are odd. So why don't we start with the case that they're both even? So if they're both even, then that means we have to calculate the probability of the first one being even times the second one being even. So that's simply 1/2 times 1/3, right? Everyone agree that's 1/6. And now let's calculate the probability of both of them being odd. So again, the first spinner is 1/2, right? 2 odd numbers, 2 even numbers, you always get 1/2. And the second one is 2/3, right? Because you have 2 odd numbers out of 3 total. So successful over total again, so 2/6. Now look at this. What is the sum? 1/6 plus 2/6. And if you do a little bit of fraction, sorry, that should be a 6 one. So if you do a little bit of arithmetic, that simplifies to 1/2, which is, guess what? The answer we got over here. So that's just another way of solving the problem. I would always go with the second solution, but it's always good to solve it another way. All right, so here's a challenge problem. So let's say that I threw 7 standard 6-sided dice. So what's the probability that the sum of the top faces is equal to 10? So I want you guys to solve this problem and tell me what the answer is. In fact, why don't we work through this problem together? Loy and Zoom user, the mysterious Zoom user, what's the first step we would take to solve this problem? Loy and Zoom user, I'm testing you guys' knowledge. All right, I suppose our grasp of knowledge isn't quite so steady. So again, this is just basic probability, right? It's just successful over total outcomes, isn't it? Right? Lloyd, were you gonna say something? I saw you like unmute in the mute. Okay, you can always type into the chat if you want. So again, it's just successful over total outcomes, right? So the total number of outcomes is actually pretty simple, right? Because each dice has 6 choices, right? There's 6 ways for each dice to decide what number it wants to be. So each dice, 6 choices, but we have 7 different dice. So that means the total number of combinations of the, like the upside numbers of these 6 dice is just 6 to the 7th power, right? Because it's 6 times 6 times 6 times 6 times 6 times 6 times 6. So that's the total number of outcomes. So if we could just find the successful number of outcomes, we could just divide that by 6 to the 7th and we'll get the answer. It's super easy. Okay, so the successful part is actually a bit tricky, but it's tricky in the sense that you have to list out numbers. It's super easy actually. Because when you have 7 dice, there's only so many ways to get 10, right? So why don't we list them out? So one way you could have them is like 1, 1, 1, 1, 1, 1, and then that's 6. See, the last one be 4, right? That's one possible case. Now, if you decide that you don't want 6 ones, then it's 1, 1, 1, 1, 1, 2, 3. Another possibility, right? Then, if you want another possibility, 1, 1, 1, 1, 1, 3, 2. And in fact, this one isn't a distinct possibility because like that's the same thing as 1, 1, 1, 1, 1, 2, 3, right? So we're not gonna count this. So now let's say that we take away another one. So 1, 1, 1, 1, 2, 2, 2. So that's 4 plus 6, which is 10. So that works. All right, so now we see that we actually can't really change anything anymore. Because if you change a 1 to a 2, you got to drop a 2 down to a 1, which is the same thing. But however, since we're accounting for, order over here, since like 6 to the 7th, so that's accounting for each dice individually and order matters. So we actually have to permutate all 3 of these combinations. But that's super easy. Because for the first one, you're just simply putting 4 in one of 7 slots. That's just 7, right? There's 7 permutations of this. It's super easy. For the second one, it's less easy, but it's basically the same idea, right? So you first give the 3 a spot. So you have 7 choices. And then for the 2, you have 6 choices. So that's 42. The remaining spots are just automatically 1. Finally, 2, the last one. So in this case, you actually have to do a little fancy combinations, but it's just 7 choose thing, right? You're choosing 3 spots out of 7 to give it to 2, right? So it's super easy concept. All right, so let's add this up, shall we? So this is 42. And the bottom one is 7 times 6 times 5 over 3 factorial, which is 6. So that's just 7 times 5, which is 35. 7, you add these up, and you get 84. So the answer, boys, is simply 84 over 6 to the 7th. And if you would like to simplify that, you can go ahead and do so. But I do not feel like simplifying that because it's a huge number. But yep, that's the basic idea. So are there any questions on this? Was any part confusing? Don't quite understand? No, no questions. All right, then allow me to show you the superior solution to the problem I was talking about earlier. Where is it? Where is it? Here it is. All right. So this concept is pretty complicated, and we would usually spend a lot more time than like 5 minutes talking about it. But this is just to give you, a brief taste of this amazing mathematical theorem that's so powerful. So what this theorem that I'm going to talk about is the principle of inclusion and exclusion. Some of you may have heard of this. I think I spelled Paul wrong. It's right here. Okay, so principle of inclusion and exclusion. Some people call it pi, but it's not a pi. It's like an acronym, like take the first capital letters from each. So basically what this is saying is that recall how if we were to calculate this probability directly, we will have to calculate the probability of the first spinner being even, the second being odd, plus the probability of the second spinner being even, the first spinner being odd. You add these together. And then, but you also have to account for the probability of both spinners being even, right? Because, it's like, because an even number can result from either one or two even numbers. So one way to do it is like that, but the other way to do it is to find the probability of the first spinner being odd and the second spinner is whatever. And then the second spinner being odd, the first spinner being whatever. And then both of the spinners being even, right? So that's basically another way to calculate it. We're not going to write it down because I want you guys to try this out. And it's a pretty advanced concept. So I want to save this problem for next class, in which we'll discuss the principle of inclusion and exclusion in further detail. So it's like you can think of it as a little teaser. I'm not going to reveal the answer today. But that's pretty much it for today's probability. Today we did really basic probability. And just to review a little bit, the principal way of calculating probabilities is the number of successful outcomes divided by the number of total possible outcomes, right? We saw many examples of this via the card problem, and also like we showed two different solutions for this, right? Because one of them accounts for order, the other one doesn't. So again, when you calculate probabilities, you can choose to whether accounting for order and possible outcomes and total outcomes, but you have to be consistent with the two. You can't vary between them. And then we saw that another way to calculate probability is simply multiply them together. You don't have to do all these like fancy big number calculations, unless you're a big number cruncher, but otherwise do the easier way. And then we give another example. And then we saw that you can also add probabilities, but this is only if it's event A happening or event B happening, right? That's when you add the probabilities. And we saw the example of this, the marble problem. And finally, we talked about complementary probability, which is when sometimes it's too hard to calculate the direct probability. You want to calculate the probability of it not happening and subtract the probability from 1. And that often makes the problem so much easier, like this one. Finally, we did these two challenge problems. And so that's it for today's lesson. Thank you so much for coming. And next week, we're not going to have class because of Thanksgiving break. So both me and you guys will enjoy a free Friday night. But unless you have any questions about probability, thank you so much for coming and have a great Thanksgiving break.